In this video, we will discuss angular acceleration. Any object following a curved path is accelerating. Anything that has a curved path has centripetal acceleration. So it goes without saying that any rotating disk, whatever, the particles that make that up have centripetal acceleration. What we don't know that they may or may not have is tangential acceleration. That is speed changing acceleration. So we want to relate to whether or not they have tangential acceleration. The problem is it depends on where they are on the object as to the direction of the tangential acceleration and its magnitude. So we want one quantity that will tell us whether or not this is occurring. And that quantity that we pick is called angular acceleration. It is very, very close, except for one word, to the exact definition that we called for regular acceleration. The angular acceleration is defined as the time rate of change and in the old linear land we said velocity, but we're not going to say velocity, we're going to say angular velocity. So we had that A was the limit as delta t went to 0 of the change in the velocity over the change in time. Back in linear land, in this case, angular acceleration, which is given the symbol alpha, the Greek letter that's the A in the Greek alphabet. Notice it's small case like our other A was, but we use Greek letters. This is related to the limit as delta t goes to 0 of the change in angular velocity over the change in time. By the way, I didn't say in the last video about angular velocity, but you know, we already used up some of the other Greek letters, so this one was pretty close to being a V, and that's why we chose to use it. It's actually a small case omega. Kind of looks like a W, but it's a small omega. And it's basically at the end of the Greek alphabet. They say from the alpha to the omega, from the beginning to the end. Well, there's the beginning, there's the end. V was pretty close to the end of the English alphabet. So that's the reason we chose those symbols. The units come from here. This is in rad per sec, and we divide by a second, so it's in radians per second squared. And again, the radian is unitless. It's only there to remind us we're in angle land. So it's really like 1 over second squared. The relationship to tangential acceleration, if you want to find the tangential acceleration of a point on the wheel, you simply take this alpha and you multiply by the radius. Notice every time we cross the border from angle land to linear land, we multiply by the radius of the circle. For different particles on a disk, let's say they're on some sort of disk here, and there's a bug, and the bug's going around like this. And maybe instead of a bug, there's a cat, and the cat's going around like this. They will share the same alpha, but they'll have different tangential accelerations because the cat has this radius, that's his R, and the bug has a much smaller r. So they don't have the same A's, they don't have the same V's, they don't cover the same arc length, but they have the same angular variables, alpha, omega, and theta. And that's why we want to describe everything on the disk with those, because one of them will describe the disk completely. Well, you need a lot of these. Angular acceleration is a vector. Just like regular acceleration is a vector, it has some direction. Now, mind you, a while back we had like cars, and the cars would have velocity like this, and they'd be speeding up maybe. And if they were speeding up, the acceleration vector would point in the same direction as the velocity. And we had cars that were slowing down. And maybe the car is traveling in this direction, but is slowing down. So since it was slowing down, the acceleration was in the opposite direction. When things were slowing down, the velocity and acceleration were in the opposite direction. When they were speeding up, they had the same direction. The same thing holds here. But it's not velocity and acceleration, it's angular velocity, angular acceleration. So if the angular speed is increasing, the angular acceleration points in the same direction as the angular velocity. And likewise, if it's slowing down, you got some sort of spinning disc or circular saw, whatever, phonograph, DVD, if it's slowing down, then the angular acceleration points in the opposite direction as the angular velocity. So if I wrap my fingers, in this case, this is omega, this is omega, by the right-hand rule. If I want to know alpha, though, this is increasing speed up here, so alpha points in the same direction. This is a decreasing speed, alpha points in the opposite direction. So if you can find omega with the right-hand rule, then if it tells you it's increasing or decreasing, you know which way to draw the alpha. Notice nothing moves in the direction of omega, nothing moves in the direction of alpha. Things move in the direction of velocity. The net force is in the direction of the acceleration A. These things do not have particles moving along those arrows. Any particle in the disk here will be moving in this plane. It will not be moving in this direction. Very important. Some important past information we've talked about at the beginning. All objects undergoing rotation have centripetal acceleration, even if they have no tangential acceleration, even if alpha is 0. If the disk is spinning at 30 revolutions per minute, if a wheel is rotating at 15 radians per second, even if that speed is constant, there's still acceleration of every particle because they are changing direction. It is a curved path. They just don't have any angular acceleration, and they may not have any tangential acceleration, but they still have centripetal acceleration. Now, when you're dealing with centripetal acceleration, we had this formula before that centripetal was equal to v squared over r. But I said, you know, if you've got like something like a disk, this particle here, he has 1v, and this particle over here going on this smaller circle, he has a different v. The runners on different size tracks have different velocities, even though they're making the around the track in the same amount of time. So that means this is different for each one of them. Their r's are different, so this is different. So this is different, this is different. It makes it hard to compare. So much better is to not write it in this form, but write it in terms of the angular variable. A useful thing is to write the centripetal acceleration as omega squared r. Every point in these guys have the same omega. So when I did it with v squared over r, I don't know which one has the bigger centripetal acceleration. But if I do it with this new formula, this one has a little r, but he has the same omega. He has a smaller r, he has a smaller centripetal acceleration. The one out here has the bigger r, he has the bigger centripetal acceleration. It will be a greater force required to hold him on out there. And if you ever played on a merry-go-round, you know that where you want to hang on a merry-go-round is on the rim, because that's where the excitement is. That's where if you're hanging on the bar, as they spin it, they have the greatest force on your arms. That's where you're most likely to slip off. If you sit in the middle of the merry-go-round, nothing happens. That's because when you're in the middle of the merry-go-round, you have no centripetal acceleration. There's no force required to make you do that. That's not exciting. You want to be on the outside of the rim. That's where it's fun to play. So this is a very useful formula. I would put it to memory as well. By the way, if you want to make sure that you see that these work, go back to this formula up here and remember that V is omega R. So then you have omega squared R squared over R. So you end up with omega squared R after you cancel those two. The total acceleration in a problem is always the sum of the centripetal and the tangential. So the total is the vector sum of the tangential plus the centripetal. This one depends on alpha r. This one depends on omega squared r. You can find the magnitude. These two are perpendicular. They're going to be like this. That's going to be the total. So that means the magnitude of the total is going to be equal to the square root of this one, which is r alpha squared, and that one up here, which is omega squared r squared. Sometimes that turns out to be a useful formula to know, but it just comes from the definition and the fact that tangential and centripetal acceleration components are always perpendicular. If you forgot that, go back and look back in our previous work in one of the earlier chapters and modules when we covered centripetal acceleration. Alright, that will finish angular acceleration for this video.